pleasure to see everybody and that people are still coming to these lectures. I appreciate that. At the end, I'll probably forget, so let me start out by thanking Tamar and Boris and Elona was early on involved in this for arranging this, and the staff, Yael, I don't know all of them, Efrat, in making this event. I think it's been a wonderful event, at least for me, and it's very important for me to see people and to come at a time when it's very difficult and to be here with fellow mathematicians and keep the lines open. So I appreciate the invitation, and I'm very happy I came. All right, thank you. So let me get into the math, which is what we can talk about. So this is a continuation, and this, in many ways, is the most elementary of the problems I've been discussing, and that is the case of just graphs. So let's look at the base node question in the case of graphs. And now, instead of looking at the Laplacian, I'm going to look at the adjacency matrix, because I want to look at gaps in the spectrum at the top, the bottom, the middle, anywhere. Some practical problems led to this, especially this work is mainly joint with Alicia Collar, who's an applied physicist in Maryland. So let me remind you, we're going to look only at 3 regular graphs. Some of these theorems, I'm sure, are true, almost all of them, for D regular graphs, but at some point we will use 3 regular graphs. She actually makes layouts and makes a device that I'll show you a picture of in a second in the laboratory, which she can only make join 3 point edges at a point, so that 3 regular is very important to her in her practical application. So everything's finite. Everything will be 3 regular graphs. I'll be going over the 3 regular graphs, looking at the base node or something like that, but we'll use the adjacency matrix, which is just some simple function. Which is some simple function of the Laplacian, but for now let's just stick with the adjacency matrix. So A applied to F, F is a function on the vertices of the graph, and A to apply to F is just all nearest neighbors to X of F of Y. I don't divide, so I don't average, so the spectrum will lie between -3 and 3 trivially. I'll assume the graph's connected, so 3 is a simple eigenvalue, and -3 is an eigenvalue if and only if the graph is bipartite. Both those are completely elementary. You just prove it with the maximum principle. The Laplacian is 3i minus a, and now we'll forget about the Laplacian because I'm going to describe the base node, which will now be at the top rather than at the bottom, so it's a bit confusing. But I want to actually ask the question, which is what she was raising when I first met her, when she started asking these questions, is what gaps we can create in the spectrum as the graph gets larger and larger. So what intervals can be gapped? And this is a very interesting question, and it's very much, well, I'll tell you some theorems, but there's still a lot to be understood here. So the gap at the top we all know, that's the expander gap. We know what the maximal gap is there, and we'll return to that. But you could ask, what about the gap at the bottom? What's the biggest gap you can make at the bottom? What's the biggest gap you can make in the middle? Can every point be gapped? And I want to answer all those questions, and they each require a different set of ideas. Let me just show you a picture of, this is what she builds in the laboratory. They're called 3 regular layouts. Everybody's trying to make a quantum device that's useful to do quantum computation. But that device there has a lot of tubes, but the layout is 3 regular, and in order to understand what happens when you input some pulse and what comes out, this gap is what's very important, and the gap at the bottom is what the problem translates to. So I won't go into this is a picture from her paper in Nature with her collaborators, but I've seen this device. I even once gave Alex Slobodsky, I didn't give it to you, I showed you. You can carry this device around with you. It's made out of lithium.
It's always planar graphs?
Always planar. I'll return to that. And that's going to be why I'm so interested when rigidity sets in due to planarity. But let's not put that condition to begin with. All right, so the base node spectrum, I showed you this picture, and I want to now give credit as to who understands the base node spectrum, which now is the gap at the top. I want to immediately observe something that we don't normally use. That is that the eigenvalues of a graph are algebraic integers, all of whose conjugates are also in the spectrum. And so Facketer's theorem that Boris was talking about is going to be irrelevant in obstructions to making gaps. So transfinite diameter or capacity might be relevant just as it was in the Tate-Honda theory in his lecture. So it's something that people do make use of, but maybe not so much use as we will make today. That is that the eigenvalues are totally real algebraic integers, and we'll use it. The base note is the gap at the top, and as we all know, the spectrum in the universal cover is minus 2 root 2 plus 2 root 2 with 3 irregular. 2 root 2 is about 2.8 something. And then we have this theorem that I put dot, dot, dot there because it's a contribution by many people, and I now want to go through who did what, just as a review. So the base note spectrum for cubic, as we defined it, is what's the closure of that set, and it consists of a discrete set. Now, remember, I'm upside down now, so there's an interval here that is, you can make limit points of the next to biggest eigenvalue under 3, and then there's a countable set here, and it's infinite, of super Ramanujan graphs. And I even, on the very first lecture, gave you that just the tetrahedron would give you eigenvalue -1, and then this thing marches up, and you can't help yourself. You have to at least accumulate here, but there are infinitely many there, and that's what the base note spectrum is. So this is a contribution of many people, and let's just review that, because there's something really exciting that happened just before the turn of the year. So at the very late moment in 2024, we're now in 2025, a paper was put on the archive that I want to tell you about. Okay, so what do we know about this? So they meant
Peter, you put also 1, you put 4 on it. So
it's multiplicity. No, that's just the multiplicity.
But you mean
They're exactly 4 with this.
only 4.
Yeah, these are all small graphs, and you can just read them from a table. Here it gets very complicated. And in fact, just exactly the gap here, how quickly it converges, that I'm going to explain right now. So for planar, if I looked at the base note on planar, we rigidify. So Gil asked, she's only interested, many people are only interested in planar graphs. You can't make a gap with planar, that's just, you can't make expanders. This is very well known, and a very concrete way of saying that is a lovely theorem of Tarjan and Lipton very early on about the cut set in a planar graph, which shows you that lambda 1 must go to 3 if the size of the graph goes to 3 regular graph. So there's no gap at the top if you restrict to planar. Rigidity immediately comes in as far as the top. The best bound in terms of lambda 1, this is the Alon-Bopana theorem quantified, it's due to Joel Friedman, is that lambda 1 is bigger than 2 root 2 minus 100 over, so the 100 is not so important, it's a log x squared there. So if you have x is the size, x is the size of the graph, the number of vertices, so if your graph is getting large, then lambda 1 must at least converge to 2 root 2, that's Alon-Bopana, but this is a quantified version. All right, so Ramanujan graphs give you the existence, as you know, of Ramanujan graphs, but the fact that there are infinitely many for which lambda 1 is actually less than 2 root 2, not less than or equal to. So if you make the construction using number theory, then there's a very interesting feature here. When you use Ramanujan, you're using that the zeros are on a circle. And that doesn't mean that you don't have an eigenvalue which is exactly 2 root 2. If there were an eigenvalue at 2 root 2, it would have to be a multiple eigenvalue, because it's coming in these graph situations, this construction is coming, say it's coming from a curve. There's a symplectic symmetry, and so there would be a multiplicity. And you might think, well, maybe I can show that you can't have a multiple eigenvalue there for some reason. And one good reason would be that if the proof of Ramanujan, which comes from the proof of Riemann for curves, would actually give you that Frobenius acts on cohomology semi-simply, because that gives you a passage to try to show that you can't have multiple eigenvalue if you see how it acts, because usually if you have a multiple eigenvalue, you don't act semi-simply, but you might. So you'd have to check that. So you have to go back and think about all proofs of Riemann, of the Weil conjectures. So Weil gave 2 proofs during the Second World War. One was a brilliant proof about involving a curve cross itself, using the graph of the curve inside of the product and counting things and using surface theory. That was elementary. That does not give you anything is semi-simple. his proof, which is a generalization of Hass's proof to abelian varieties, his proof which uses the Jacobian as an abelian variety, actually proves that Frobenius, it's the only case where Frobenius is proved to be semi-simple. And so that's what you could use, and that was used by Coleman and Eidixhoven to show that if you look at certain of these weight 2 modular forms, you can show that 2 root 2 doesn't occur as an eigenvalue. And Nina Zubralina used that and gives, you can see lambda 1 is less than 2 root 2, but exponentially close, but you can make infinitely many Ramanujan graphs which are super using arithmetic, and I'm just saying that you're using Weil, it's critical. Weil's, that proof of Weil. Deline's proof in general does not give the semi-simplicity. His standard conjectures would, but those are not proved. So we don't know that because Deline's proof uses higher and higher symmetric or some symmetric powers, and you never prove the zeros are on a circle. You prove them that the higher the power, the closer to the circle. So
But beta theory doesn't give you something better?
not really, no. Anyway, we can have much better results here. The only issue was, is the set, I'm interested in the base node, and I want to know there are infinitely many discrete eigenvalues, discrete points in the spectrum, just because I love Markov spectrum, and there are infinitely many Markov points above them, so we have them here. Now, there are some other proofs. This is the stop press proof. I'll get to that. There's Marcus Spielmann and Srivastava, who give a proof using interlacing polynomials and Li-Yang theory. And their proof, which is, when they make this, it only works with bipartite, but when it works, they do better than this. In other words, they will be able to prove that lambda 1 is less than 100 over absolute x. Remember, this is the limit from John Friedman. So that's very nice, but they don't make Ramanujan graphs which are non-bipartite. All right, this is, before I get to the stop press, the issue of being dense, I'm still explaining this, that you're dense here, that is to say you can always find a sequence of graphs whose lambda 1 converges to any number between 2 root 2 and 3, because the base node spectrum was a closure. That was proved only recently by Nogalon and Fan Wei, whose joint work with me and Alicia Collar we'll return to. The argument's very nice. It uses work of H.T. Yao and Wang, that if you not only is the random graph almost Ramanujan, but the eigenfunctions are in the random graph, the eigenfunctions are delocalized. And because they delocalize, they don't localize anywhere, and you can go around changing the graph a little bit to force lambda 1 to change on a finite dimensional space and make any limit where you want. So the key ingredient in this work, which makes a limit everywhere, is this delocalization theorem of H.T. Yao and his student Wang, and maybe there was this third order here. But the big breakthrough here, which was just put on the archive 2 days ago, is a fantastic theorem of Mackenzie, H.T. Yao, and Wang. I have a bet with Noga Alon many, many years ago, is the random graph Ramanujan? And he said yes, and I said no, and we're both wrong, and now it's proved. The random graph, non-bipartite, meaning now we have for every degree D a graph which is Ramanujan in the proper sense. So this completely, as far as existence majorizes this, is 69% Ramanujan. Where does this come from? So this is pushing this random analysis to its limit, but it was clear already in 2002 that the number's going to be somewhere between 0 and 1. Usually you think it's either going to be 0 or 1, but it became clear to me, and we had an REU, me and Stephen J. Miller, and 2 students, one of whom is Novikov's, not related to the famous mathematician Novikov, but another one, where they checked numerically. So how can you come with a theorem like this? What do you prove, and what did they first, where did this conjecture come from? So you look at lambda 1, and you look at its fluctuation as you take, you do numerics. You take a random walk on 3 irregular graphs and 100 vertices, and you look at what lambda 1 looks like. And it'll look close to 2 root 2. So you take lambda 1 minus 2 root 2, and you look at the statistics, and you divide by the sample's variance size, which turns out to be some power, like in longest increasing subsequence. That's where this theory is coming from, is Tracy-Widom distribution. And it was quite natural to expect that that would converge to a Tracy-Widom distribution, which is some probability distribution discovered by Tracy and Widom in random matrix theory, which has the property that it's got some mass on the right and some mass on the left. And the mass on the right would give you the Ramanujan at the top is about 89%. And then independently you condition also that the bottom is, we're making proper Ramanujan on both sides. And that's in this proof they shows the independence, so you multiply two probabilities and you get 69%. So that's the theorem, and that is an absolutely stunning theorem, and I've been waiting for it for 20 years. And HTR got to the exponent 1/3 at my 70th birthday in the summer. It was clear to me it's just a matter of time, and they delivered. This is a major result. Okay.
And this we say is sharp probably.
Oh, and by the way, sorry, and it gives 2/3. Yeah, what, sorry?
And this is what you think is the
No, I don't know. So it's between log and 2/3. I don't know, I wouldn't. That's what the random, this is sharp, this is what the random gives. But there may be rare events where it's better. Yeah. But for the typical guy, that's it. So as far as, I guess I have to pay Norga a little bit, because it's 60. But I'm a mean guy, so I'll make him pay me. By the way, it was always clear that he was wrong, because the number was going down. You do numerics, it's going down. So I said, goodbye, you finished. But does it go down to 0? No, it stops at 69%. All right, so I want to discuss the possibility of making gaps elsewhere. So I'm going to discuss the gap at the bottom, which I'll call the Hoffman gap, because there's some very beautiful constructions here. And there's a very beautiful paper that is not appreciated enough that I want to explain, because I want to...
Can I stop you for
Yeah.
a minute? Up to now, is there any of these results which you have a reason to think that it's not true for general D?
No, this is all D. No.
No, that's all D. I know.
Everything's D. Up till now, everything's
Except
any
of
D.
the well, I guess the Ramanujan is P+1. Or
Yeah.
plus one.
Right. So our stuff is always prime power plus 1. This is prime power plus 1. These are all any D, correct. Yeah, I just
But
stated.
eventually, I don't. Do you see a reason that the final results that the bus, what you call the bus spectrum, is between Ramanujan and the top?
No, they prove that for any D.
and discrete to the left.
That's-
This is you believe.
No, they proved that's a theorem. So
No.
this is true for any D, even though I just stated for 3.
So now this is true for every
Every D, yeah.
because of the last.
Yes, because of the last thing.
Ah.
Yeah.
The arithmetic
Yeah.
Ramanujan graphs. You proved, they proved it 1.3 to the power.
No, this is Nina just used that and then a crude bound. She tried to use something a little stronger from Baker, but didn't get anywhere. Yeah.
But do you believe it's the right value?
No. This is very crude. It may be, somebody should check numerically. Maybe these Ramanujan graphs do as well. I don't know. This is what's proved. Okay, let's look at the bottom. So there's a lovely observation of Hoffman that when you take the vertices and the edges of a graph, any graph, you can look at the incidence matrix, which is a m by n matrix, where m is the number of edges and n is the number of vertices. And if you take that matrix times the transpose, you get an n by n matrix. And if you take that matrix in the other order, you get an n by n matrix. And the spectra of these two matrices by linear algebra are the same except for the kernel and the co-kernel. And that means that there's some relation between the spectrum of, when you take the adjacency, this incidence matrix in the other order, you get the spectrum of the line graph. So a line graph of a graph is you take the vertices and the edges, they're the vertices of your new graph, of your line graph, and the edges and the guys you connected are the ones, or all the edges which connect each other at a vertex. So it's called the line graph. And so the spectrum of the line graph, the adjacency matrix spectrum of the line graph, is given explicitly in terms of the kernel and co-kernel, which is -2 to the number of edges minus the number of vertices, union the spectrum of -2i, the adjacency matrix of Z, plus the diagonal plus D, not minus here, plus D, Z, where D is the diagonal matrix associated with the graph Z. So this is true for any Z. It doesn't have to be irregular. Okay. So if you do this, you immediately see this is non-negative. That's easy. So that the spectrum of a line graph of any graph is always between -2 and infinity. Always. And you can see what's at the bottom. If that's got no kernel, then it's -2 to some multiplicity. And this Hoffman observed. And once you see this, then you get into this situation where, using the Rayleigh quotient definition of the minimum eigenvalue of Z, we're now looking at the minimum eigenvalue of the adjacency matrix, not the maximum, which is the whole expanded story, which everybody loves. We look at the minimum, then we don't have anything at the bottom. We don't remove, we don't talk about lambda 1, we talk about the smallest eigenvalues, just this minimum. And from just if I have a induced subgraph, let's call it B, then just taking zeros at the induced subgraph, I have a quadratic form with fewer constraints. So you get this kind of inequality that lambda min of Z is less than or equal to lambda min of any B for any B induced subgraph of Z. So if we want to see whether a subgraph has eigenvalues below -2 or any value at the bottom, there are going to be many B's that are not allowed because we can compute small B's and they are not allowed. So there's subgraphs, there's a whole structure of not illegal subgraphs which you can immediately remove. And this is kind of the situation where you should expect by kind of a Seymour Robinson kind of philosophy that there's a clean theorem. And there's an absolutely clean theorem here. And it's this theorem which I think is not celebrated enough. It's a theorem of Cameron, Goethals, Seidel, and Schult, 1975, called line graphs, root systems, and elliptic geometry. And what they prove in this is they show that for any graph, they want to know graphs which have eigenvalues less than so any line graph has this property, and they classify that if this property is true, then you must come from a line graph or a cocktail party graph, some generalization of that, or some finite number of sporadic examples which exist in E8 as a subset coming from a Cartan matrix interpretation with this number 2. Okay, I think this is a fantastic theorem, but let me show you I'm going to use it, or we're going to use it, Alicia and myself. So I'm going to define a map from the cubic graph to the cubic graphs, which is going to be critical in understanding many, many things concerning gaps. So I start off with a cubic graph. If I subdivide, I take each edge and I take the midpoint and I put new vertices. Okay, now the graph is 2, 3 regular, because at each vertex that was before it's 3, and now at the midpoints I'm 2, 3 regular. And then I take the line graph of that. If you think about it, you'll see it's 3 regular. And so you'll start off with a graph and you'll make a new graph which is 3 times larger. And all you're doing when you work out what you're doing is you're sewing in a triangle, equilateral triangle at each vertex. But because I've gone through this line graph construction, I'll know something about the spectrum of this. So I start off with a graph, I make a 3 times larger connected graph whose spectrum is going to be related to the guy I started out by some rational dynamics that we're going to study in a second. And that will allow us to understand this question. All right, so in this paper with Carla and her physics collaborators, we proved the following, that suppose, now I'm looking at the gap at the bottom. I'm looking at all 3 irregular graphs, and I want to make the gap at the bottom as big as possible. So this guy's always extremal. The complete graph, just that we've seen, has lambda min -1, so that's bigger than -2. And otherwise, if you have all the eigenvalues greater or equal to -2, then we use their classification to show that the graph that you're looking at, if it's large enough, must be in the image of this map that I just defined for you. That is, if there's a very large graph, all of whose eigenvalues, so the bottom of the spectrum is -2. So of course I'm going to tell you the spectral gap at the bottom is 0, -3 to -2. And I'll even tell you when you hit the end here, so it's much simpler than the top. But the statement is exactly this. So let me repeat. The spectral gap, the biggest gap you can make at the bottom is 0 minus 3 minus 2. And if you have a graph which is large, which has its smallest eigenvalue minus 2, it must be in the image of this map T coming from this line graph construction. So it's on the orbit of this infinite system. I'll ignore this because you can try to see the next limit point, but I want to get to the things I want to discuss. All right. So the real problem I want to study now is not just at the bottom. So that solves the problem, the gap at the bottom. It's really Hoffman's work plus that amazing theorem of Cameron et al.
But it can be much larger than what you would get in the
And they plane. Right?
uniform on the universal cover. Like it can be much. It's not.
So on the universal cover, the spectrum is minus 2 root 2. So yeah, correct. So the biggest gap you can, yeah, that's correct. You can't help yourself but make eigenvalues near minus 2. That's, you can't make the gap bigger than minus 2, and if you make it as big as minus 2, and you actually, so this problem is understood much better than the gap at the top, because we know the extremals come from, they're infinitely many, they all, you can make them planar, and they come from starting with a planar graph and just keep on applying this map T. I'm going to be using that to answer the following basic question. All right, so now I ask a general question, which I think is a very natural question. Sorry, here's a question. So I'll say an open set in minus 3, 3, that's where the spectrum is going to lie. An open set is a gap set if there's an infinite sequence of graphs which have no eigenvalues in U. And I'm very interested in what gap sets you can create and a maximal gap set. Can we actually answer these questions? So the question you might think is the natural one is, can you hear the shape of a graph or something? What are the eigenvalues? But those usually don't have nice answers. They counterexamples and things like that. And they don't give reconstruction of the graph from the set. The practical problem that we've seen at the top, which is the expander, and at the bottom, which Alicia wanted, that's exactly what you want to know, the biggest gap at the bottom, are questions where you force a gap on with more and more, where your graphs are bigger and bigger. So what's the biggest open set? What is a maximal gap set? I think that's a definition. The complement of that, sometimes I prefer to state it this way. I give you a closed subset of minus 3, 3, and I'll say it's a spectral set if you can find an infinite sequence, all of whose eigenvalues lie in this closed set. So that's just the dual, the complement. And then this is the most important thing that she wants to know is, can you make a gap at some point? Is every point gappable? So I give you a point, can I find a neighborhood and then an infinite, that neighborhood might be very small, such that there's an infinite sequence of 3 regular graphs which have no eigenvalues there. So what gaps can you create? And this is just an extension of the expander problem with the optimal and the bottom, the Hoffman problem. And in chemistry, I'll show you in a minute, the gap in the middle is what they're interested in. What's the biggest gap you can make in the middle between minus 1 and 1, for example? Okay, so that's the problem. And since there was a discussion of Honda-Tate theory and Fackett's theorem, which was a bit out of order in the lectures, but very well received, let me tell you that this is exactly the same as the following. So suppose I give you the zeros of a zeta function of a curve on a abelian variety. So they proved that all the zeros on, this is the reciprocal of the zeros, they lie on a circle of radius square root of q. If you're coming from a curve on a abelian variety, if you come from a curve, you have some symmetry, so they're symmetric, but that's not an issue here. And we can ask the same question. We fix q, and we let the genus go to infinity, either the dimension of the abelian variety or the genus of the curve, and we ask, what gap set can we make inside? Can we make big gap sets? It's completely the exact same question. And this has been asked and answered by Sarah recently. Actually, Sarah is quite advanced in age, but not, his mind is still there. So he still writes beautiful papers. And this from 2019. And here's the answer. So firstly, for curves, there's a rigidity. So you cannot make gaps. It's a theorem of, you more or less didn't get into the Jacobians much in your talk, but It's a theorem of Fassmann and Vladut, that is, if you fix Q and you let G go to infinity, these will have to become dense. So it uses it, you're coming from a curve, because if you're coming from an abelian variety, then it's a problem about numbers whose all of whose Galois conjugates lie in a set. And then the only obstruction is capacity. So I'm going to define capacity right now. But this is Sarah's theorem, that if you have any subset of the circle whose capacity, so this is rigid, and this will be not rigid. And we'll see in the graph case, the problem's much more complicated. But it's the same kind of question, and capacity comes in. And I remember working with Alicia on this, and I woke up one morning emailing her, I think capacity is irrelevant to what we're doing. And then I thought, I've seen this before. And then after a number of hours, I said, yeah, Sarah's writing about it, and he's already observed that in this problem, it's capacity. It's not going to be decisive like here, but it's going to be one of the constraints in making gaps for graphs. And a very important constraint. But here it's completely decisive. So Sarah's theorem is if you have a closed subset, let's say a finite union of intervals, whose capacity is bigger than the q to the quarter. So the capacity of the circle is, I'm going to define capacity in a minute. Capacity of a circle radius q is square root q. So if the capacity is bigger than q to the quarter, roughly the square root of that. So the set could be rather thin, could be many intervals, and it's not just the measure, it's a measure relative to potential theory. Anyway, if the capacity is bigger than q to the quarter, then you can find an infinite sequence of abelian varieties, all of whose eigenvalues lie in, that's a spectral set for zeros of zeta functions. So he's answered that problem completely there. Here's what capacity is. It's defined by Fekete as transfinite diameter. Then there were many works showing that it's the same as some potential theoretic definition. But this definition is very clean and very clear why it would be related to placing the conjugates. So I'm going to state the theorem of Fekete. Suppose you have a compact subset of the plane, its diameter or capacity is you try place your points as far as possible, n points as far as possible inside the set, so that their geometric mean is as big as possible. So that's this dnk, if you put n points. And it's very easy to see this function is decreasing, so it's got a limit, and its limit is called the transfinite diameter. It's also equal to the capacity. And computing capacities is not easy. But we do know that the capacity of an interval in a circle of an interval is its length divided by 4. Chebyshev proved that, basically. And the theorem of Fekete, which is at the heart of Sarah's theorem there, is that if you have a compact subset and the capacity is less than 1, then it's just a matter of, we saw this in, I think, your talk or in maybe Smith's talk. If the capacity is less than 1 and you have an infinite sequence of algebraic numbers, all of whose conjugates lie in K, then and the capacity is less than 1, then you can't have an infinite sequence. So put it another way, if you have an infinite sequence, the capacity must be greater than or equal to 1. That's called Fekete's theorem. And Raphael Robinson, the husband of Julia Robinson, who was himself pretty good, proved a converse to this, which Sarah uses, and that is if the capacity is bigger than 1, then you can find, and it's real, then you can find an infinite sequence. He constructs an infinite sequence of algebraic integers, all of whose conjugates lie in K. Now, there's something called Honda-Tate theory, which more or less converts this problem to the problem that Sarah's looking at, so he uses Robinson. So Sarah reduces, some people call these Bay numbers. I'm not a fan of that. But I think that passage here is kind of clear of how Sarah gets at. And what we saw, which is a major breakthrough of Smith on a conjecture of Smith, Smith, and also we'll hear a lecture later today, Orlovsky and Sardari have solved this for non-real and much more, is the following. You might ask, well, what limit measures are there on K? So the set version of what spectral sets are for zeros of, or for Weil numbers or zeros of zeta functions of abelian varieties, you could ask, well, make the probability measure, which is the sum, this should be the minimal polynomial, sum over the zeros, 1 over n, you've got a probability measure, and you can ask, what are the weak limits there? And there's this amazing insight of Smith, Chris Smith, that if you have any integral polynomial, and this is used to do some very nice things, if you have any integral polynomial q, this comes from a resultant computation, that the integral of log q against any weak limit of such measures must be non-negative. And what Alex Smith proved very recently and gave a lecture about it last 2 days ago here, is that this condition here is necessary and sufficient for real guys, and for non-real, this is what they've proved. So this is a quantitative version. That doesn't mean we know what all these measures are which satisfy this, but this varying Q here allows you to do serious stuff, and it's, I would call it a quantitative converse to Fekete. All right, so now I'd state the main theorem concerning what we know about cubic, and then I'll start restricting to planar, and then start restricting to fullerenes, because I want to see how things rigidify. Okay, so any spectral set has capacity at least 1. I mean, you can guess where that's coming from, and that's because the eigenvalues are algebraic integers, all of whose conjugates are, and if you take the minimal polynomial, so you have to worry about minimal characteristic polynomial, and that takes some combinatorial proof. But that's a restriction. If I give you any subset of -3 whose capacity is less than 1, you can never make an infinite, that can never be a spectral set. But that's not necessary and sufficient here, very far from it. But that's a necessary condition, so we should keep it in mind. A purely combinatorial theorem we can prove is that any interval whose length is at most, whose length is bigger than 2 cannot be a gap set. So let me repeat that. I give you any sub-interval of -3, 3, and if its length is bigger than -2, what? Its length is bigger than 2, yeah. Its length is bigger than 2, it cannot be, then there are only finitely many 3 regular graphs which have no eigenvalues in that set. And that's sharp in the sense that we'll see 2 kinds of intervals which are length exactly 2, so they are maximal gap intervals. And those are the kind of things that I'd really like to understand, the maximal gap intervals. That's when you've understood what gaps you can make for 3 regular graphs. There are planar graphs. This is probably the hardest part of the theorem. Every point in -3, 3 can be planar gapped. Now you might tell me that sounds wrong because you can't make a gap at the top. Now, if I choose, I've not got 3 here. So if I take a point which is tiny little bit less than 3, then I'm allowed to make a lot of eigenvalues to the right of that and to the left. I'm allowed to take a small neighborhood. And that's the hardest part of our proof, is to deal with points very near them. I'm going to explain the methods, and I'll outline something about the methods in a second. This is purely combinatorics. This is rational dynamics. This is an example coming from this transformation T, which is also used in both of these. And these are examples that we find by hand. Maximal gap sets. All right. So maybe let me say a few comments about the proof. So the lower bound on the capacity is Fekete. I don't need to say much more. It's just a matter of minimal versus characteristic polynomial, and that takes a combinatorial proof. The upper bound, that's what you're asking.
What's the capacity of an interval?
The interval divided by 4. So -2 is much bigger. Yeah. Okay. So you're not getting it from that. This -2, the length 2 thing is a purely combinatorial theorem. In other words, what we show is, of course, the graph is going to have to get large. I don't know whether it's getting skinny or long or star-shaped. I don't know what it looks like, but it's going to have some kind of long diameter, long geodesic, which is going, and we build an approximate eigenfunction around it, and the number 2 is miraculously related to building something locally around along such geodesic in the graph. So this is purely combinatorial. And probably the most interesting new thing to me was that to gap every set between -3 and 3, we use firstly some abelian covers which allow, so there's something called Bloch wave theory, which, by the way, the solid state physicists, so Alicia's got this code that will, you input a graph and some abelian covers, it will compute for you all bands and gaps in abelian covers. So you can make bands and gaps in abelian covers by using what's called Floquet theory or Bloch wave theory. And she's got a program that just does this instantly and allows us to make many examples where we have big gap sets. So remember, I'm trying to gap any point. So I need to take any point and find explicitly a gap, infinite sequence which gaps it. Or when we get near 3, it's going to be very hard to make, because the gap has to be very small. So we have to do something clever there. And so what we do is we make a lot of basic examples using Floquet theory or Bloch wave theory. And then we use this transformation T to move it around. So there's a formula for the spectrum of T of X in terms of the spectrum of X. There's a polynomial, a quadratic polynomial, whose inverse image, so the spectrum of the T of X is the inverse image of the spectrum of X union, you saw those 2 points, new points that come out. So each time you apply T, you get these points with high multiplicity, and then you get a new, you have to take the inverse of sigma of X. So if you want to know what you do when you iterate this many times, you quickly land up looking at the rational dynamics of this map. That happens to be quite an easy one to study, and we study it. There's something called the Julia set, and the Julia set is actually a spectral set. Let me skip that, but I'll just say that rational dynamics for this quadratic polynomial, and in particular that when you restrict F to the Julia set, it's actually a topologically isomorphic to a shift on 2 symbols, and that allows us to move this gap as close to 3 as we want.
This is a point where 3 is important.
Yes. Yeah.
What F will be if these?
Okay. So the minus 2 and 2, minus 2, 2 is very restricted to D equals 3.
Because of this function?
No. This generalizes. You can sew in other things. So this part will be okay in general. The gap, we'll be able to gap anything, but the fact that minus 2, 2 is the biggest interval in minus 3, 3 will change, and this building of a thing around a 3 regular graph is much easier than building it around a 4 regular graph. So this part is not, this part is general. And in fact, I'm going to show you something where there's we're not just going to need this one, we're going to need much more. Anyway, this is an easy one to study. I've already explained if you take this set, this Julia set, it will be a set of capacity 1. I want to point out that there is a set of capacity 1, which is a spectral set for planar graphs. And that's because that Julia set is a closed set, and I have an infinite sequence of graphs, all of whose eigenvalues lie in this weird Cantor-like set, and it's got capacity 1. There's a very nice formula for the capacity of a set after you operate with a rational map, especially first coefficient 1, as that one is. All right, these are examples of planar graphs, which I'm now going to discuss the many parts to this theorem. This minus 1, 1, and minus 2, 0, because I want to end and spend 15 minutes on this and fullerenes, which is really juicy. Okay, so how do we make, so this, we cannot have a bigger interval which is spectrally gapped, but how do we show that there's an infinite sequence of graphs which have no eigenvalues in minus 1, 1, or 2, 0 is similar? And the construction is, here it is. There's some abelian cover, and there's some, this is a planar graph, which is 3 regular, and we can show the spectrum lies between, there are no eigenvalues in minus 1, 1. And that shows that minus 1, 1 is a maximal gap interval, because it cannot be bigger. But recently somebody, 2 people who I don't know, Guo and Royal, 2024, actually classify all 3 cubic graphs which have no eigenvalues in minus 1, 1. Completely. So they show that the sequence we made, which is this one, planar, and another sequence which was made before by one of those authors, and Moha, are the only infinite sequences which have no eigenvalues in minus 1, 1. I'm going to return to why minus 1, 1 is so interesting. And then there are 15, if I'm counting correctly, other ones. And So they completely classify that. That's really a decisive theorem, very beautiful theorem. It's kind of what you want. These are those infinite, and then here's some funny ones.
There was a lot of computer calculations to find the sporadic set.
Yeah, the papers involve computers.
Peter,
Yeah.
I have a question. Can you go back to
I haven't studied the paper deeply enough. Yeah.
the spectrum of a line graph of a graph? You have this f minus 1, and then you have minus 2 and a 0.
Yeah.
Minus 2 and 0 have some geometric
Yeah,
interpretation.
they keep on getting added in, and
You
with
can
high
get
multiplicity.
explicitly,
Yeah, it's got a cohomological interpretation, absolutely.
Yeah, so can you make use of that to like ignore them somehow when you make spectral analysis?
You could remove them and talk about only proper limit points, not, when you talk about a limit point, I forget what the definition of a limit point is. Is it distinct points going to the point? Or anyway, there's a lot to do here. The most interesting thing is to find maximal, minimal spectral sets or maximal gap sets. That's a decisive theorem. So minus 1, 1 is maximal gap. And I'm now going to, I should have said there's another example of a maximal gap set. And this uses this beautiful theorem of Glasner and Aubert and Virag. This is a minimal spectral set. So Ramanujan graphs put all the spectrum in the set. But maybe you could make a gap inside there. Is that a minimum? You might think, well, maybe I can find some very clever graphs which are firstly Ramanujan and then eat out in the middle. Why not? Because I'm asking for the minimal spectral set. What's the minimal set? So this is not trivial. It's a beautiful theorem of Glasner and Aubert that if you have Ramanujan graphs like this, then they Binyamini-Schramm converge to the 3 regular tree. It's a converse to Ramanujan. And you're not assuming the girth gets large. So when I showed this to Sarah, he said, oh, that's in my paper. And I said, no, you assume the girth gets large, and then it's trivial. So this is a very beautiful theorem. And it says that this is a minimal spectral set. You can't make any other gap.
And
If you're greedy and you want to be Ramanujan, you can't make more gaps. Yeah.
And if you slightly relax the Ramanujan, like Ramanujan plus epsilon, would this fail?
Yeah,
Or
I think so. Well, does it?
is Ramanujan condition necessary for this result?
The theorem is, they assume Ramanujan. I don't know if it's necessary. I think, so you can't relax it too much, that's clear. All right, anyway, I just wanted to point out that this is a non-trivial theorem, that's a minimal spectral set. So anytime we have the complete answer, we're very happy. Okay, so the question is, how does rigidity enter? And rigidity means that you can't make gaps anywhere. And the minute you put the condition of being planar, then
This theorem with these quadratic examples, there was no planarity assumption.
there's no planarity assumption, but the graphs we make are planar and the other ones are not. And that'll be important here. So once your graph is planar, then there's only one way of realizing it topologically as planar. This is well known. And so you can talk about the faces and in the planar realization. And you can try to see whether you can make gap sets once you restrict the number of sides per face. Now, if you restrict the number of sides per face to be less than 6, then Euler's formula will say there are only finitely many such things, so that's not interesting. But k equals 6, there are infinitely many, and this is a beautiful set of 3 regular graphs. They're also triangulations of the sphere of degree at most 6, and that's the dual statement. And Thurston studied these, F6, and he called these triangulations, or the dual he called them triangulations of non-negative curvature. And he proved an amazing theorem that it's a very difficult theorem. He proved that these triangulations are in 1-1 correspondence with the orbit of a group. He doesn't point out it's arithmetic, but it's a lattice inside SU91, which turns out to be arithmetic. And there's a 1-1 correspondence between the orbits of this group on level sets where there's a Hermitian form of an imaginary quadratic field which is fixed, and the number of orbits there is the number of such triangulations, or in our language would be the number of elements in F6. And he did that because there was all this stuff about buckyballs and things like this that I'm going to return to in a second. And he wanted to give an upper bound for the number of triangulations of a certain type, and he wanted to get k to the ninth, n to the ninth as the upper bound. But he's giving the answer in terms of arithmetic. An arithmetic group, he doesn't point that out, but it's an arithmetic group. And this is a highly non-trivial theorem using cone points and moduli space of flat metrics, and it's kind of orthogonal to all the stuff that people do in Teichmuller dynamics. It's kind of the opposite side and just as interesting. I mean, anytime you get a lattice inside SU91, Mostar then picked it up and then wanted to see is it arithmetic or not, because he was looking for non-arithmetic lattices. We don't know in SUN1 whether non-arithmetic lattices. Of course, it's arithmetic, or you would have heard of that. I think what's the biggest dimension for which is non-arithmetic for SUN1? 3 is certainly Deligne Mostar.
Even
4, maybe 4 is not even that. Okay, so there's a big change when k, this is something that in the work I'll describe, there's a big change from k equals 6 to k greater than equal to 7. Now there's a fantastic subset of the guys which have at most 6 sides per face, and those are the ones which have exactly 6 sides, hexagons, and only pentagons. And those are something that chemists are extremely interested in. They're called fullerenes. And they've been trying to count the number of fullerenes, their atlases, and they study these. Here's the example. Of course, this is a football. It's a Ramanujan graph, and it's got pentagons and hexagons. This guy is smaller. It's only got pentagons. This is a mixture. Now, once by Euler's formula, there'll be exactly 12 pentagons, and all the other ones are going to be hexagons. And you can count how many of them, and you can ask what spectral gap you can make for this. Now, there's a spectral gap that's important to them that goes back to Huckel theory right in the beginning of chemistry. You have high orbitals, high energy orbitals, low energy orbitals when you fill with energies to try and understand the stability of some molecule like carbon. So these things are studied, and in this high energy, this Huckel gap is the gap in the middle. So if you have a 3 regular graph, the number of vertices is exactly 2n, so they're an even number of eigenvalues, and the gap in the middle, which is the gap between the middle guy and the next to the middle guy, they want to make as big as possible. That'll make this carbon cluster as stable as possible. So here we have a problem where we're trying to make the gap in the middle big, and the question is, what gap can you make there? And so the question, if the thing were bipartite, the middle gap would be symmetric around 0, but there's no assumption like that. So anyway, these are these things here. And I want to tell you a fantastic theorem. This is a theorem that blew my mind. This is an application of the Siegel-Wey theorem, which I view as beautiful as Jacobi's formula for the number of ways of writing a number is the sum of 4 squares. It's an exact answer. It's the sum of d divides n of chi of d. And we love that. That's kind of where automorphic forms comes into number theory. So you can ask, how many fullerenes are there on 2n vertices? And this has been looked for years. And here's the exact answer. It's an Eisenstein series. It's the sum d divides n of chi3 of d of some polynomial. This is completely explicit. All right, the coefficients are a little horrendous. But it's an Eisenstein series. The number of fullerenes on 2n vertices is given by an exact sum of divisors, as you would in the theory of Eisenstein series.
And this theorem is Thurston?
No, so Thurston reduced the problem to something in SU91, and the 2 people doing this are Peter Smiley and Phil Engel, and an appendix by some guy who does a lot of numerics to check that this is correct. And the theorem is they use what's called the Siegel-Wey formula, which is they want to count the number of these orbits, and this thing is class number 1. So some adelic integral is always an Eisenstein series. That's the main theorem in the Siegel-Wey formula, which is usually for orthogonal groups, is for unitary groups. They revisit all that, and the answer is an Eisenstein series, no cusp forms, completely elementary, and this counts the number of fullerenes. I think this is just a fantastic formula, 21st century Jacobi formula, and the proof is the same. By the way, Siegel developed the whole theory of Siegel modular forms in order to give automorphic proofs of his mass formula, of which this is an example. And then his student, Hal Brown, did it for Hermitian. So the whole theory of the Ziegel-Wey formula, which, by the way, when I was here in 1987, Ilya and his group were calling it Wey's formula, and I said, no. And they actually listened to me. Now it's called Ziegel-Wey, because Ziegel had done it before Wey, I can assure you. Just Wey had put it in the right conceptual way. Anyway, these guys go and they actually compute from scratch and use to me it's clear that you're going to have such a formula, but they actually get it, and it's a tremendous achievement. This doesn't answer my question of what the gap is for fullerenes, and that's our main theorem. And this is joint with Fan-Wey as well, and we're still finishing it up. I'm the culprit of slowing it down, so I feel very bad about this because I'm running around the world. So, can you gap every point with something in F6? No. We're going to explain that. But if you have F7, we believe that you can gap every point with planar graphs with limited number of faces. But we don't know how to prove that. We just can prove it if you have at least 64 sides or more per face. And our proof is the same proof with the rational dynamics replaced by much more complicated polynomial dynamics to sew in things which don't increase the number of faces when you apply the t. If you just apply t itself, it's no good. Okay, so here's the key rigidity. If you go to F6, those are planar, remember the planar graphs with at most 6 sides per face. Then we rigidify that the only, you can't keep any, you have to get eigenvalues between -3 and -1 and between 1 and 3. They have to start to become dense. And you can make this as a gap. So the planar set that we have there allows you to prove this with 6. But the real question is, suppose I now put that I want, what gaps does fullerenes have? What gap set can you make with a fullerene? Because that was a question that chemists were really asking. And it turns out there's a fantastic answer that we prove, and this is quite involved. There's a subset, so with fullerenes you're obviously going to only be able to gap a smaller set. So there's a number A, which is algebraic number that's given from our proof, which is roughly -0.3 something. And there's a unique number in the middle there that cannot be gapped.
That's probably -A minus B, right?
No. It's the same B. It's not symmetric. No, it's -A to B can be gapped, and then B to A, the same A, can be gapped, but B itself cannot be gapped. And that's the biggest interval with that property. So we completely understand what the gap set for fullerenes is.
How do you show something?
Yeah, something like that is shown by a whole elaborate one-sided fullerene cap. So you start with hexagons and these nanotubes, and then you want to put at the end some pentagons. And we sew in pentagons, and we have study a one-sided eigenvalue problem like this that has a bound state with this eigenvalue, and it can never be get rid of. It's like, so it comes from the proof, and it's very pleasing. And we're still writing up the complete proof there. So there's a very tricky part, which is sewing in very carefully these pentagons, which is non-trivial to sew in a pentagon. And we use some theorems of chemists about fullerenes to do that, and some numerics that they do to prove something. Anyway, the one thing we don't, so the rigidity comes in. Let me just end with this. There's a question here at the end. I want to point out that we don't solve, so this is this capping argument that I was saying about, and this was this nanotube, so I just don't go into that. But let me just point out that there's one thing we don't solve. In our construction, we have this interval, and there's a point in the middle. But the trouble is the middle guy, we know that the middle guy shifts to the one side, and so we do not know whether you can create a gap in the middle for fullerene, which is the problem that they were most interested in at the time. I don't know that they're still interested in it, but at the time it's a great mathematical problem. So the question is not what's the gap set, which we've understood, but can you make the gap, the middle gap between the two middle guys not go to 0 when n goes to infinity, or can you keep that gap open, which would mean some stability of what's called graphite. That's a limit of carbon. So that was a question that they asked, and we don't know how to answer that because our theorem does not, in our theorem, in these constructions, which we would have maybe showed that you can keep the gap open, those have the property that the guys in the middle go to one side, and the gap between the middle and the next to middle goes to 0, but another gap is open. And so we know, in terms of minus 3, 3, exactly that interval with a 1 point removed is exactly the biggest interval you can ever gap with an infinite sequence of fullerenes, but we don't know about this middle gap. So it's clear that there's much more to understand in this kind of problem. It's much more difficult than the problem that Sarah was looking at, where you have a billion varieties. And of course, you can go through all of these and start asking about quantitative versions of it. You know, if you make the measure on the eigenvalues, what's the possible limits? So that's used a lot to show that certain gaps cannot be arranged. And then to make other gaps, you actually have to be able to find a reason in the gaps that you've seen, like minus 1, 1, we make them by construction. So that's the story for prescribing here. And of course, you could ask this question in any locally uniform geometry. And I think it's clearly an interesting question, not just the base note. I want to just make clear that the rigidity theory of Margulis and the 7 authors says that the problem of making a gap inside the tempered spectrum is not a problem. Because you always, let me just repeat that, so doesn't exist here. All this rich stuff is because you're not Binyamini Schramm converging to anything like a regular tree or something. So in those cases, you always Binyamini Schramm converge to the universal cover, and the spectrum of the universal cover is already the Plancherel measure. You have to become dense in the Plancherel measure. You can never make any more gaps. But in hyperbolic surfaces, you could say, well, can I make a gap between 7 and 8 with an infinite sequence? And I'm sure you can. I just don't. It's an interesting question. Because they are very, so these very, they don't Binyamini Schramm converge to the universal cover. They're like long sausages or things like this. Okay, and thank you for listening, and very happy to be here.
Can you say in 1 or 2 sentences why chemists care about this type of problem?
Because it's the stability. So if you ever take molecular chemistry, they're always drawing hexagons and joinings. And the Huckel theory of molecules, before people started solving Schrodinger's equation on computers, they tried to understand whether some molecule made out of carbon molecule or something will interact with another one. And the stability of that, is based on the gap between what are called HOMO and LUMO, high energy modes and low energy modes. And so if that gap is big, and that's a good heuristic, I think, for small molecules, we'll say this, they'll put it in some solution and it won't interact with anything else. It'll be stable. So that's the reason. And so the mathematics out of that is this gap in the middle. So, of course, you and I love the gap at the top. There's a gap at the bottom that Lisha needs for something else, which I didn't explain. And there's this gap in the middle. But once you're asking about mathematically, you should ask what gaps can you prescribe. And that's what this question is. And the answer is probably very difficult. I don't expect a complete answer. These are the maximal gap sets. In fact, even by Zorn's lemma, it's not even clear how to talk about a maximal gap set.
What is the asymptotic number of fluorescence?
Yes. Yeah. So it's what it's d to the 9 or whatever. Yeah. Yeah. It was the sum of d divides. Yeah. Where's my? Yeah. You should like this. I asked you how many triangulations there are with. Yeah. So this polynomial is degree 9. So it's. And some d divides n, forget that, n is the biggest guy in this case. N to the 9, n to the 9.
The other factor.
They're smaller, d to the 8, d to the 6, but this is exact. Okay, you ask ChatGPT to guess this. Do me a favor, you like this ChatGPT, and it'll get it because this was just put on the archive recently.
But this is very small compared to the number of triangulations.
No, this is what Thurston wanted to show. The number of triangulations with 6 sides is only polynomial, and with 7 we prove in our paper that it's exponential. And I think it's the first proof that it's exponential. If you like all triangulations, then it's exponential. But if you take even 7, we prove it's exponential. So 6 is a changing point and rigidity sets in. And the whole point is at 7 we think there's no rigidity. So you can't gap every point. So if you're trying to make a planar graph and you want to make a gap at some point which is not between -1 and 1, you can't gap it. Yeah, so the number of triangulations was all that Thurston was trying to show you. He wanted to show that the number of triangulations is polynomial. Then he says, many people say that the number is exponential if you have no restriction. But I'm telling you, if you fix 7, it's already exponential. So this is really a changing point. But, I mean, Thurston, I knew it quite well. He said, no, I don't want formulae. So this would have, so he was just order of magnitude.
Didn't go into the 9?
He did. That's what he concluded. He didn't. He said they at most n to the 9. He wanted to show it's polynomial. He had no. He had the exponent. That's all.
He had the right hand.
Yeah, of course.
But this is just the simple version of the formula. If you sort of do it without this congruence condition, it becomes more complicated.
If you start putting now, this passage is highly nonlinear. If you started with the coordinates, which are these planar triangulations, and try count and see maybe conditions. If you try to do equidistribution here, the coordinates are very different, and there's some very interesting problems. But this problem of using Ziegler-Vey, these two guys, I was blown away. So what happened is I gave a lecture on this without knowing this. I was lecturing on the fact that the spectrum, and this guy Phil Engel comes to me and says, am I familiar with Thurston being able to count these in terms of SU91? And I knew the paper, but by the way, this paper is not, there are very few people who understand it as far as my people who I'm involved with. It's a very hard paper to understand. Mostar rewrote versions of it, but he starts straight into the group. He doesn't talk much about the triangulations. So there's a passage which starts off with, roughly the way he proves it is you have 12 pentagons, and all the hexagons have the property that if you put a flat metric on them, the hexagon has the angle so that that's still flat. So there are going to be 12 places where you're going to have singularities, cone singularities with some prescription. And then he studies the moduli of space of such cone singularities. And then, of course, Thurston doesn't, he wants to prove there's some group here, so he's got some local moves called butterfly moves, which are in SU91 transformations taking you from one place to another, and he shows the quotients finite volume with these butterfly moves. And Rick Schwartz is one of the few people who's gave a whole course and some exposition on this. It's a beautiful paper and not so well. It's not like, as I said, the thing that has Teichmuller dynamics has much more attention paid to it. This is the same theory, the same philosophy. That you. Schwartz has got notes which, yeah, I mean, this formula. He loves this formula. But it is Jacobi's formula. It's something is an Eisenstein series.
Yeah. Can you just give out why people care about the gap at the, like why she cares about the gap at the bottom?
Yeah, okay, so there's another tight binding hopping model in solid state physics, which when you make the weights on various edges equal, you get a graph. And the gap that she needs in terms of transport, whether this device she's making conducts or does not conduct, depends on the gap at the bottom, because the Hamiltonian is not the Laplacian, but it's some operator on the line graph. So she's already working on the line graph, and this gap that they have is something the line graph gap is something that's very useful to them. So then the question is, what's the maximum gap on the line graph? And that turns out to be this. So if you read out my paper with Alicia, then we refer to her Nature paper where this is explained. Yeah.
If chemists are interested
They were. A Nobel Prize was given to it, called buckyball.
Yes, they don't care about quarks. But you waste.
No, but they've got an atlas where they try to make new fullerenes from old. So they've got all sorts of moves, forget what they're called. That make new, bigger ones from old ones. And they try to, the atlas tries to classify all of them up to size 200. So they've got the exact count, which these guys check to make sure that their formula is correct. That's where the numerics involved there. Now they do care about, because especially these things, at that time anyway, these things were new kind of materials with some very important properties. Enough that a Nobel Prize was given on just for the soccer ball. Everything in the soccer ball is like a good guy. Yeah, it's called C60. Yeah.
Can you understand the spectra by the action of this group?
Which group? No, I don't. No. So I don't know. So the degeneration. I didn't know how many of these there were. All I was studying is the degeneration as you go to the boundary. So our proof more or less does some kind of degeneration to the boundary, and that's where this bound state that's in the middle comes in. So we're studying how nanotubes degenerate and how their spectra, so without counting and without knowing first. So your question is there some way of using number theory to see further? That would be fantastic. So far it's just doing the counting. And counting is, it's lovely when you have an exact formula. Now you can see I'm excited by this formula.
More questions? Let's say it's been
Wow, you should thank all the speakers.
So much for coming.
Yeah, thank you.